Land degradation is one of those environmental crises that just creeps up on you. It's not a sudden event.
It's a slow-motion catastrophe.
Exactly. We're talking about losing that essential layer of productive topsoil. And when that goes, everything else starts to fall apart. Soil fertility, water quality, and the region's entire ability to feed itself.
And it has knock-on effects. You get more sedimentation in rivers, you lose vegetation, farm yields go down. It really destabilizes the whole ecosystem.
Okay, so for this deep dive, we're going to zero in on a really fascinating and threatened location, the Sylhet Hair Basin in northeastern Bangladesh.
It's an amazing place. Ecologically vital, incredible biodiversity, but it is under massive pressure.
What kind of pressure are we talking about?
Well, picture this. It's a tropical monsoon climate, so you're getting rainfall that can top 4,000 millimeters a year.
Wow.
Yeah. And you combine that incredible amount of water with things like deforestation and some unsustainable farming practices, and you've just got a recipe for severe soil loss.
And that's where this research comes in. The mission was basically, how do you take this massively complex basin and create a practical roadmap for conservation?
A shortcut, really. Instead of getting bogged down in all the data, the researchers used geoinformatics, so that's GIS and remote sensing, to digitally map out the whole area.
And what did they find?
They analyzed 18 smaller areas, or sub-watersheds, and the headline finding is pretty stark. Get this. Almost 43% of the total area falls into the high to medium priority risk classes for soil erosion.
43%. So nearly half of this vital ecosystem is actively degrading.
It is. And the really high-risk zones, the ones that need immediate help, make up 11% of the area. That's over 1,000 square kilometers.
So our mission here is to unpack how they figured this out. We'll look at the two key layers of their analysis: the physical terrain, which they call morphometrics, and then the human activity map, or LULC, to understand why these areas are at such high risk and what can be done about it.
Let's start with the place itself, the Sylhet Hair Basin.
Tell us about it.
So it's in northeastern Bangladesh, part of the big Meghna River system. It's also in an active tectonic zone. But what really defines it are these things called hors.
Hors.
They're huge, kind of bowl-shaped wetlands. They're absolutely essential for holding floodwater during the monsoon. But that massive rainfall means that rapid runoff is, it's the main villain in this story.
And because it's so complex, you can't just treat the whole basin as one big problem.
Exactly. That's why they use watershed management. You break it down into smaller, manageable sub-watersheds. It's like triage.
And they combine two big data sets to do this.
Right. First is the morphometric analysis. That's all about the physical terrain, the shape, the slope, the drainage. It tells you how naturally vulnerable the land is to erosion.
Okay, so the inherent risk.
And second is the LULC analysis, land use-land cover. That's where you overlay the human element, where the cities, the farms, the cleared land, the man-made drivers of erosion.
So how do you take all that data stream length, soil type farming and turn it into a simple priority list?
They use a method called the weighted sum priority. It calculates a single score for each sub-watershed, called the compound parameter, or CP. But here's the key thing to remember, and it feels a little counterintuitive at first.
Okay.
It's a reverse ranking system. The sub-watershed with the lowest CP value gets the highest priority for conservation.
Wait, so the lowest score is the highest risk? Why do it that way?
Because what the CP value is actually measuring is the sub-watershed's stability. So a high score means it's stable. A low score means it's unstable, highly sensitive, and therefore it's a top priority for intervention.
I see. That makes sense. It's a measure of vulnerability.
Exactly.
All right, let's dive into that physical blueprint first, the morphometric analysis. This is the land's natural tendency to erode, even before you factor in human activity.
So first, you look at the drainage network, like the plumbing of the basin. They found this hierarchy where you have 95 tiny first-order streams.
The little trickles.
Right, the little trickles and tributaries. And they all eventually feed into just one single large fourth-order stream.
So a lot of small inputs feeding into one big outlet.
And that structure, that dominance of small streams, it tells you that water collects and starts moving in channels very, very quickly. That points to huge surface runoff and a really high potential for flash floods during the monsoons.
Okay, let's talk about the key metric here, which is drainage density, or DD.
Think of D as how densely packed the plumbing is. A high value means you have a lot of stream channels in a small area. And that usually points to steep slopes, maybe impermeable soil, and crucially, very fast runoff.
So where was the plumbing most, let's say, problematic?
One sub-watershed just jumped off the page, SW11. Its drainage density was an incredible 30.23 kilometers per square kilometer.
30. That sounds ridiculously high.
It is. I mean, just based on that one number, SW11 was immediately flagged for urgent intervention. Its physical structure is just primed for erosion.
And why does that high density matter so much?
It's all about how much time the water has to soak into the ground. Not much in this case. We can link that dB value to other factors, like the length of overland flow. A low value there means water travels a really short distance before it's funneled into a channel and starts picking up speed. Places like SW11 and SW5 had very low values, which points directly to steep slopes and, well, much higher erosion.
So the water basically hits the ground running.
That's a perfect way to put it. And that speed is directly related to another number, the infiltration number. SW11 also had the highest score there, about 80. A high number means very low infiltration. The ground just isn't absorbing the water. It's a perfect storm created just by the terrain itself.
It's incredible how geology and elevation can just multiply the risk.
Yeah.
But the shape of the watershed matters too, right?
It absolutely does. The shape influences how quickly water is discharged. For instance, SW10 was almost square-shaped. Basins like that tend to release all their water at once, leading to a high peak discharge and more erosion.
And what about the opposite? A long, thin watershed.
Right, an elongated one. That would have a low circularity ratio, like SW8 did. That suggests a less developed drainage system, but still a higher potential for erosion overall compared to more balanced shapes.
Any other red flags from the physical analysis? What about flood risk specifically?
Well, the overall stream network seemed pretty stable, but there was one interesting anomaly. The ratio between the third and fourth order streams was really high, a 7. That kind of spike can indicate a structural weakness in the drainage system, making those specific areas much more vulnerable to flooding from rapid runoff.
Okay, so we've got a clear map of the natural vulnerabilities. But of course, erosion isn't just a natural process. We need to layer in the human impact. That's the LULC analysis.
This is where it gets critical because you're bringing human activity into the equation. And a few land uses really stand out as erosion drivers. The biggest one, built-up areas.
Urbanization.
Yeah, roads, parking lots, buildings. You're basically paving over the landscape, creating these impervious surfaces that stop water from soaking in. That just dramatically increases the volume and the speed of the runoff.
And which areas were feeling that development pressure the most?
Subwatersheds like SW6 and SW8 had really extensive built-up areas. We're talking over 35 or 45 square kilometers. Those places need immediate structural solutions to handle all that runoff.
And what about land that's just bare?
That's the other major driver. Barren land, like they found in SW14 and SW17, is naturally exposed. There's nothing holding the soil in place, so it needs immediate surface protection, things like planting or mulching.
But it's not all bad news. Some land uses actually help stabilize the soil. Right?
Oh, absolutely. Well-managed agricultural land like in SW1 and SW4 can be quite stable. And of course, dense vegetation, which was prominent in SW3 and SW7, is a huge stabilizer. The roots hold the soil together.
And the water bodies themselves, the hearers.
They're crucial. They act as natural sediment traps. The water slows down and the soil it's carrying gets deposited there instead of being washed further downstream.
So we have the physical risks and the human pressures. Now we bring it all together with that compound parameter to get the final priority list.
And this is where you get the full picture. A few subwatersheds, SW11, SW12, SW5, and SW6, they were consistently ranked as high priority in both analyses.
So they have the double whammy.
Exactly. They have intrinsically sensitive physical terrain, like steep slopes, and they have intense human land use on top of it. They are, without a doubt, the most vulnerable zones that need top-tier attention immediately.
And this is where combining the data really shows its power, because I imagine it uncovers risks that one analysis alone might miss.
This is the real aha moment of the study. Take SW4. If you looked just at its physical morphometric score, it was medium priority.
Okay.
And if you look just at its LULC, its land use score, it was also medium. But when you combine them, the compounding effects, like decreasing vegetation, push it firmly into the high priority category.
So the combination revealed a hidden threat.
A threat that two separate studies would have completely missed. It proves the value of this integrated method. The whole is truly greater than the sum of its parts here.
Did it work the other way too? Did any areas seem less risky after combining the data?
Yes, SW9 is a great example. Based on its land use alone, it ranked as high priority. Lots of human pressure.
Right.
But its physical terrain is actually quite stable, gentler slopes, well-developed drainage. So when you factored that in, its combined rank came down to a stable medium priority. That's vital information for deciding where to allocate limited resources.
And it also tells you where not to focus the most urgent funds.
For sure. The study consistently flagged SW3, 13, 14, and 16 as low priority. They have stable physical traits and more sustainable land use. In a way, they serve as a benchmark for what stability looks like in this basin.
Okay, so the final step is turning all this data into actual on-the-ground advice. The researchers are clear. You need hyper-specific strategies. One size does not fit all.
Absolutely not. You have to tailor it to the land use, the soil, the slope. So let's start with those high-risk agricultural zones.
What's the prescription there?
For places like SW3, 4, 6, and others, you need targeted farming methods, things like terracing and contour plowing, which physically reshape the land to slow the water down.
What about something like cover cropping?
Cover cropping is huge. The study recommends it widely because it can slash erosion by anywhere from 30 to 90%. It's a low-cost intervention with a massive payoff.
Now, for the built-up areas where you have all that concrete and asphalt, you need a totally different playbook.
Entirely different. There, the focus is on green infrastructure. We're talking about rain gardens, permeable pavements, things that are designed to absorb water instead of letting it run off.
And those have been shown to be pretty effective.
Very effective. They can cut runoff by 50 to 80% in urban areas. For these zones, you also need things like retaining walls to stabilize critical slopes next to roads and buildings.
And for those barren, exposed lands.
There, the goal is just rapid surface stabilization. So you're looking at reforestation, afforestation, maybe hydroseeding or mulching, anything to get roots in the ground and a protective layer on the surface as quickly as possible.
Does the advice get even more specific when you drill down to soil type?
It does. For areas with loamy soils, they recommend contour farming. But for those with heavy clay soils, you need to physically break up the compacted surface to help water infiltrate. So you'd use techniques like subsoiling or planting grass strips.
And finally, for the absolute steepest slopes, like in SW9 and SW14, I imagine that requires heavy-duty solutions.
It does. You need fully engineered solutions there. We're talking deep-rooted vegetation planted specifically for stability, engineered terraces, and retaining walls. The risk is just so acute that you have to bring in the structural reinforcements.
So when you step back, what this study really provides is this incredibly rigorous, data-driven framework. They've taken a huge, complex region and broken it down into these manageable action zones, each with its own specific prescription for healing.
And what's so powerful is that this very local specific work has global relevance. This directly supports the UN's Sustainable Development Goals, specifically SDG 6 for clean water and SDG 15 for life on land. By stabilizing soil in this one basin, you're building long-term ecological resilience.
It really hands policymakers a precise map and a toolkit. But we always like to leave you with a final thought to chew on. This research gives us the what and the where. But future work needs to integrate other factors, like climate change projections, which will likely mean more intense rainfall, and, critically, the socioeconomic side. We know what techniques work, but how do we make sure that these solutions, which can be costly, are actually sustainable and fair for the local communities living and farming in the Hara Basin? That's the next complex human challenge that needs to be solved.